Welcome, students. Today we will study M.Sc. Final Chemistry, Paper First, Unit Photochemistry, Excited States, and Jablonski's diagram. Myself, Dr. Sudha Sukhwal, Shringi. Let us first study excited states. So, two types of excited states are there: singlet state and triplet state. Singlet state. A molecule is said to be in singlet state if all the electrons in it are paired. It is represented by symbol S. Triplet state. A molecule is said to be in triplet state if all the electrons in the molecule are not paired. It is represented by symbol T. The terms singlet and triplet arise from the fact that singlet states do not split in a magnetic field, while triplet states have three possible energy states in an applied magnetic field. There are an even number of electrons in a typical organic molecule, and these electrons are usually paired in the ground state. Absorption of light of the correct energy occurs without spin inversion, and so the electron spins remain paired in the excited state. This state is commonly called excited singlet state or S1. However, in many cases, electronic excitation is followed by spin inversion, thus giving rise to a new excited state with two unpaired electrons. This state is called an excited triplet state or T1. Direct excitation of the ground state S0 to a triplet state is not possible, and hence T1 is invariably populated via S1. These processes can be visualized for the ethylene molecule, in which absorption of light of the correct wavelength promotes one of the pi electrons to the pi antibonding state pi star. So have a look at the figure. Singlet and triplet states are shown. So S0 represents ground state. Electrons are paired in the ground state. S1 is excited singlet state. T1 triplet state. Electrons spin remain paired in excited singlet state S1, and in T1 electron spins are parallel. A triplet state is more stable than the corresponding excited singlet state because the two electrons do not get very close together in space when their spins are parallel, and hence lesser interelectronic repulsion is expected with unpaired than with paired electrons. We'll now study modes of dissipation of energy, major events that occur following light absorption by a molecule, or in exam question can come, give Jablonski's diagram, describing dissipation or decay of energy from higher to lower levels, or describe photophysical processes in electronically excited molecules. Let us now describe the major events that occur following light absorption by a molecule, thus raising it to a higher electronic state, say from S0 to S2. S0 is ground state, S1 singlet excited state, T1 triplet excited state, S2 upper excited singlet state, IC internal conversion, ISC intersystem crossing, F fluorescence, P phosphorescence, RD radiationless decay. Straight line represents transitions with absorption or emission of radiations, and a zigzag line in waveform represents radiationless transitions or non-radiative transitions. So have a look at the figure, the possible routes to loss of excitation energy. So I'll suggest you to make this diagram, Jablonski's diagram first, and then we will discuss all the points in detail. So if you will have the diagram with you, then you will be able to understand it very easily. A molecule on absorption of radiation is excited from the ground state S0 to S1. From S1, there may be further excitation to S2. S2 represents the higher vibrational level of the upper excited singlet state. The lifetime of upper excited singlet state is usually less than 10 to the power minus 11 second, and they rapidly decay to the lowest level S1 by a process called internal conversion. Decay of S1 to S0 may also occur, but it is usually a slower process than decay from higher electronic singlet states S2 etc. to S1. So consequently, S1 has the longest life, 10 to the power minus 8 second, of all the excited singlet states, and is very important in photochemistry. S1 undergoes energy losing process in one of the following ways. It may emit energy as a photon and revert to S0. This is fluorescence. And it generally occurs within 10 to the power minus 9 to 10 to the power minus 6 seconds. It may return to S0 by non-radiative processes in which excess energy of the excited state is shuffled into vibrational modes. S1 may undergo chemical reaction. It may undergo fragmentation, or it may drop to T1 state by intersystem crossing, ISC. Although the conversion of S1 to T1 is energetically gainful, it is rather a slow process in accordance with the spectroscopic rule that change in multiplicity is formally a forbidden process. However, if the singlet state is sufficiently long-lived, as in the aromatic and carbonyl compounds, the S1 to T1 change called intersystem crossing occurs with a high degree of efficiency. Let us now describe probable paths for T1 states. A T1 state may not be converted to S1 again since T1 is of lower energy. However, it may either undergo a chemical reaction or it may return to S0 by radiation-less decay RD. It may drop to S0 by emission of photon, this is phosphorescence P. It may undergo fragmentation. All these consequences of the absorption of light are summarized in the figure. Since S1 and T1 states differ in energy contents and electronic distributions, they are expected to possess different chemical and photochemical properties. For example, the S1 state of butadiene undergoes valence isomerization, while the T1 state, attained by energy transfer, prefers to dimerize. We'll study these in detail later. So, now we'll see what is intersystem crossing. It is an important phenomenon in photochemistry as T1 exists for a much longer period of time, 10 to the power minus 3 to 1 second, than a singlet state, and so photochemical reactions are favored by the longer life of the T1 state. ISC is more efficient in the molecules where the energy gap between S1 and T1 is small. So, a typical example is benzophenone. In this case, intersystem crossing has 100% efficiency because of the small energy gap, that is 5 kilocalorie per mole. Have a look at the figure. S0, S1 and T1 states are shown. So you can see the energy gap is 5 kilocalories per mole. So the intersystem crossing has 100% efficiency because of the small energy gap. Now many aromatic ketones and other aromatic compounds have high intersystem crossing efficiencies, while there is high energy gap in the two states of olefins. So they have a lower tendency to intersystem crossing. Thanks.